Nice of you to read that out. Hey everyone, I'm Joeri van Leeuwen from Astron. So the summary of my talk is already in this picture right here. We used Apertif LOFAR 2 interferometers to study the FRB sky. FRB found the bursts, 24 of them, often very short high DM bursts. Some of these bursts, you can see it in the colors here, they emit over multiple frequencies. This is an artist impression. And for the ones that show low frequency emission, we were able, for some FRBs, we managed to also detect them with LOFAR. And this is important because that means that there is no electron mist around the FRB emitter. It means that these FRBs, some of these FRBs get emitted in very clean environments. So, that sounds like Lego. So, you can be part of this if you're a student. So the first student that asks me a question, either here or on Slack, they get this Lego Apertif. Yeah, they're very limited edition. Yeah. So wait, wait, at the end. If you. All right. So fast radio bursts. So we used interferometers, Westerbork and LOFAR. These can both do imaging and time domain, and keep an eye out for imaging results that are coming out soon, where the field depth of both Apertif and LOFAR is very comparable, and that's going to be quite great. But I will talk about time domain mostly. So if you crank up the frame rate on these interferometers, so here is an artist impression where we show you what happens if you crank it up to 20,000 frames per second, because that's what we do on Apertif, then what you see is that in some of these individual frames, a bright pixel will appear. And these pixels are sometimes individual bursts from neutron stars or radio pulsars, and then they're galactic. But sometimes they're extragalactic, and then they're FRBs. Now, this is intriguing. I have a background in pulsars, because already in pulsars, we don't really understand how they get to be so bright. So to have sources out there, far out in the universe, that are so much more luminous is mind-boggling. These must be uniquely energetic. So I put this in this plot here. Actually, the screen is not tall enough. So here at the bottom, I plot the pulse width and the bandwidth of pulsars and FRBs, and they're very similar in this ground plane. But then if you go on this axis, which is the luminosity, this is 10 to the 10 times brighter. So there's some real unique energetics going on in these FRBs. 1 millisecond FRB contains at emission as much energy as the sun puts out in a year. So I'm interested in finding out how that works. So we use Westerbork. We're now early FRB detections were with single dishes, but now we're moving into interferometers, and with SKA and ngVLA, this will get even more. We outfitted 12 of the Westerbork dishes with PAF, such that we get a good field of view, and we still retain the sensitivity and the localization capabilities of this interferometer. So a couple of lessons learned that we came up with early, I want to start with, and then I'll do some other lessons for ngVLA and SKA at the end. The data rate of this interferometer is so high, this machine produces more data than the internet of the entire country of the Netherlands. And so this means you got to do it all in real time. There's no way to store it. And so that has a number of interesting implications, but the real lesson learned was we needed to build a hybrid supercomputer, to do real-time RFI excision. We needed to do real-time FRB search called AMBER, part of which is going into SKA. And we needed to pioneer candidate deep neural net selection. But the interesting bit of this was that this made us leaders in the field of data-intensive real-time machine learning work, and this actually came with its own interesting funding and work opportunities. And so Apertif is a main part of a big program in our national science agenda that I'm the PI of, and that's really all about real-time machine learning. So again, one lesson learned is if you want to explore new parts of parameter space for our universe, then sometimes this comes with benefits because there's an interest in by funders and computer scientists. Next lesson learned is, so CHIME is an amazing FRB finding machine. one of the benefits of an array with dishes that can steer and point is that you can spend more time on especially interesting sources like repeaters. And you will still get all the one-off FRBs too, because these happen all over the sky. This is the final impact of our survey plan, but you can also see that we operated for 2.5 years. We started in 2019 and finished in 2022. I get this question every now and then. So Apertif is done, yeah? We're no longer operating it. And the third lesson learned is not one that I usually bring up, but it struck me a few days ago. These are very tangible and visible and impressive machines that look out into the universe, and we feature them a lot in our TV and YouTube outreach. We have good connections with kids' TV shows, and we make new shows almost every year. And you can see sometimes they're about exoplanet searches through eclipses, but sometimes about aliens or about optics. And these get shown in every classroom in the Netherlands. We basically have 100% coverage over all elementary school kids, and this has been amazing for STEM, I think. All right, FRBs. So this is the first FRB detection. On the left-hand side, you can see the beam pattern, if you will. The central beam is where the FRB went off, and these chromatic side lobes is where it didn't appear. And on the right-hand side, you can then see the ellipse. The ellipse is much smaller than the circles that you would get if you didn't make the array beams. But you can also see that the localization is really mostly good in the east-west direction. This is a 1D array. This is the downside of using a 1D array. You get localization in one direction mostly. Often, though, this is good enough to come up with to determine the host galaxy, because you have also some idea of the distance. So overall, we found 24 new FRBs, which was a good addition to the total number overall, but especially because these have good localization. And some of the other things that were interesting, I think, was because we really cranked up the back end, it made a lot of sense. The frame rate was very high, the channel bandwidth was very low. We had less trouble with selection effects that some other telescopes may encounter. And so we, in my opinion, we saw the real FRB sky, which is very narrow, very high DM. And also we had localization. I'll go into the narrowness in a bit later. So here's some of the interferometric localization that we managed to do. This is an FRB that will show up in Inés Pastor Marzuela's paper. That's our second batch of FRB detections that will come out in a few months. And you can see here that if in the red, again, you have the localization ellipse of the interferometer. Then if you take into account also the dispersion measure that we have, and you do a probability analysis, then it turns out that this host galaxy G1 is over 80% likely to be the host. So we found 24 FRBs, and some of them are of special interest. So I want to just touch on a few themes. 7 of these have multiple components. And so this means that even though the FRB itself is only a millisecond, if you really zoom in, if you take 80 microsecond samples like we do, then it turns out they have a personality. And so if I was a student, I would ask the speaker about this at the end of the talk. What does that mean? One is especially interesting. Especially interesting because CHIME has recently found, a few months, maybe a year ago by now, an FRB that has, I think, 9 components, and these are spaced periodically, I think 6, 7 sigma, so that gives you an idea of the underlying mechanism. I think there, I should have checked that, I think there the separation is 200 milliseconds or so between the bursts. But in this case, we find an interesting source in which the separation is only half a millisecond. So half a millisecond, 2 kilohertz. It's not inconceivable for a neutron star spin, but if it really was a spinning neutron star, it would be strictly periodic. And then the periodicity, or if it was the last bit of emerging neutron stars, it would also be strictly periodic, and it's not. If you do the periodicity analysis, then it's not even 3 sigma. Now, so in one sense, this means it's not a result, but in the other sense, it's actually really interesting because we have a lot of other mechanisms in coherent emission that are also quasi-periodic. In pulsars, we have things like microstructure, the pulsar shows this too, where you have quasi-periodic behavior. So this suggests to me that an FRB like this could be made in the magnetosphere of a strongly magnetized neutron star. Some of the other interesting bits are the scattering. In principle, we think the emission of the FRB, when it gets sent out, it's like a delta function, so you can still see the sharp rise in this source, for example, and it should be followed by a sharp decline as well, but you can see an exponential decay, and that's because multipath propagation affects some radio photons took the long way around, and that's why you get this exponential tail. Now, what's neat is that if you, and so we know how much the scattering increases if you go to lower frequencies. And so we know that if you extrapolate this to chime frequencies, for example, then a number of these FRBs would be missed, according to the selection effects that chime themselves think that their telescope shows. And so again, I think this, even though this is 2,000 sample, there's hundreds of FRBs now, thousands. This is a pretty unbiased set, which I think is interesting for population studies, which we do too, but I don't have time to go into that. So 3 of the FRBs are especially interesting. There's a little animation of one FRB coming and going through the halo of M33. They're getting extra dispersed. Now the one in the top, the dispersion of this FRB is increased by also local electrons, and now the one in the middle. And so we had 3 FRBs go through the halo of M33, and hence also the halo of M31. Here's the real image. You can see the optical size of the galaxy on the bottom right, and 2 of the FRBs go even within 20 kiloparsec of the center of the galaxy. And so this allows us to count the otherwise invisible electrons along this line of sight. So this is a really interesting way of determining, if you know the ionization fraction, of determining how much baryons, how much mass there is along this line of sight between the host and us. And so here is one of these DM budgets that you can then do, where you can see the FRB in the background. The vertical axis is frequency and the horizontal axis is time. So here is a 1 millisecond FRB, but it still takes 500 milliseconds to go through our band. And this delay becomes important later, so keep that in mind. But if you do the budgeting of this DM and you go from left to right, from local to far away, then first you have the contribution of the interstellar matter over our Milky Way and the halo, and these are numbers we know quite well. And then there is a set of numbers that we don't know so well, but now at least we have an upper limit on our total. We know there is a hot gas bridge between the Milky Way and M31 and M33, and this probably adds about 100 DM units, parsec per cubic centimeter. In this budget, then there's the halo itself. Then finally, there's the IGM behind it, and then there's the contribution of the host. This host contribution, as we've been hearing earlier, is hard to estimate, but now, at least for this source, we have for the first time an overall, for the M33 halo, we now, at least for the first time, have an overall limit on how much dispersion is added, and that's less, it must be less than 500 parsecs per cubic centimeter. So very briefly, I want to say that one of the other interesting things that came out because of this fast and well-sampled system is that we found some of the highest DM FRBs, and then if you calculate the redshift, this must mean the FRB was emitted in its rest frame around 6 gigahertz. If far away FRBs do this, then local FRBs must do this too, and this has really restarted my interest in higher frequency FRB searches, and I think for SKA band 5 and ngVLA this will be interesting. So if we then go to the other side of the energy spectrum, we get the low frequencies at LOFAR. So Apertif is a fully real-time system, and this means that, and they both are operated out of Astron, and this means that we could connect the real-time system at Apertif to LOFAR. I was saying earlier that this example FRB takes half a second to cross through L-band, and then sometimes it takes a minute for the same FRB to reach LOFAR. So you have some time to prime. And so we did that. We pointed the Westerbork dishes now at a known and repeating FRB, 2018-09-16b. Well, a little bit sadly, whenever we saw Apertif bursts, nothing showed up in the LOFAR band. This is a 16-day periodic FRB though. So strangely, a few days later, when we were still simultaneously observing, all this was completely simultaneous, there were no Apertif bursts. But then suddenly LOFAR bursts appeared, and this was a big deal. We all remember the day quite well in the team, because no FRB had been seen at these low frequencies before. We had even already concluded that FRBs cannot get out. We had really, I in my mind had already concluded that FRBs must always be surrounded by some young supernova remnant that blocks the low frequency radio emission, and had kind of given up on using them as cosmology tools. But now it turns out you can do it. And so this means that some FRBs at least, and we heard this earlier, live in clean enough environments that we can use them for cosmology. So every 16-day period, we would see Westerbork bursts for 2 days, and then we would see LOFAR bursts for 3 days. And so this difference in duration and the delay is actually the opposite of one of the main models we had at the start, which is that the periodic FRBs are emitted by some straightforward binary wind, stellar wind in a binary. And so that's not it. This is the same thing, but now in a plot. So binary wind models don't straightforwardly work, but we do see that ultra-long magnetars can still work. All right, that's it. So welcome to the era of interferometers for FRB research. We showed that if you do full coherent searching, we've made more tight array beams than SKA mid will. You can get a good range, a good rate of FRB discoveries with excellent localization, with good localization. And we use this to map the magneto-ionospheric content of our universe along these lines of sight. Thanks.
All right, questions.
You got to say you're a student, otherwise it doesn't count.
Hello, I am a student.
Sweet, congratulations. Okay, can I say, so if there's also someone on Slack, you can do that too, and I'll mail it to you. Yeah, this is to the Slack audience. Yeah, okay, please.
That was a really cool talk. I have a lot of questions, but I'm only going to ask one. 3 or 4 bursts going off like in the M31 region out of 24, like what are the statistics on that? Did you look into that?
The statistics are pure luck. The statistics are that one of our calibrators, so it's fine statistically, but the reason is one of our calibrators is in Triangulum, the galaxy. And so because we found our first FRB in Triangulum, and I was saying earlier, because we are a pointed steerable dish array, we can choose where we point. So we basically then want to figure out, is this first FRB a repeater? Yeah. So we go visit that field again to see if it's a repeater. Then a second FRB goes off. Then you have 2 reasons to stick on that field because you want to know if they're repeaters. And then a third one goes off. So in principle, in some sense, it's luck. The first one was found near M33. We put our energy in there, and then we found a number of sightlines. So in that sense, it was a good, we had a lucky break.
Wow, that's really cool. Thank you so much.
Let's see. Right here, and then we'll do Joe.
Don't fight.
We've got a lot of time. I saw this hand first, then we'll come to you, then we'll go in the back.
So I'm a student.
Okay, maybe.
But I would be happy to give it also to somebody else. I was wondering, for the 3 FRBs, like, it's completely not my field, but can you get a rotation measure for that? And with that, then an estimation of the magnetic field in the halo?
Yeah, no, that's very good. For someone who's not an expert, you ask good questions. Yes, so I didn't go into that here, but one of the really bright FRB for which I showed the DM budget, it also has an RM budget. And that one is really strange. The halo of M33 does not add a lot of RM. Also, the other background sources in that field, they have low RMs. This one has an RM of 600. And this must almost, like 90% of that must come from its host. So so that FRB does live in a complex and active magnetic environment, I think.
Okay, great, thanks.
Oh, yeah.
Finally, I'm a student too.
Yes. Should have brought a bigger bag.
I have a question about Westerbork, actually.
Yeah.
As far as I understand, Westerbork is going to be decommissioned, right? So you're not using it anymore after Apertif, right? So I was wondering, well, I'm doing this question to every people I meet from Astron or Jive. But is there any plan to still use the wall array, or to, I mean, to
No, I
fund it?
understand. I understand your question perfectly. So Apertif stopped operating. So Apertif was on 12 of the 14 Westerbork dishes. Yeah. So the paths are not operating. We're slowly physically decommissioning those at the moment. 2 of the remaining dishes are always used in EVN, and they will continue to be operated like that with the multi-frequency front ends. What's next for Apertif? What is next for Westerbork? We don't know. It's a good, in principle, a good radio quiet site. Of course, it has some of the same challenges that many of us have with satellites and RFI. So that part is to be determined.
All right. There are 2 more questions. So there's one here and then one in the back. Who has the mic? You got it. So you're up.
I'm also a student. But my question pertains to when you said they're very narrow, right? We know Crab is one of the pulsars in our Milky Way who can emit very narrow bursts in terms of nanoshots and giant pulses. You can imagine Crab as a low luminosity version of what it is, right? Whatever class of pulsar that is. And it's getting really close to the M81 luminosity, M81R luminosities. Is there some inclination of how LOFAR can maybe say whether or not they're crab-like things?
Yeah, no, very interesting. So we had 2 papers out. One it just came out on Archive a few weeks ago with the first set of FRBs of this 24. And there's I think 7 FRBs in there, and 4 of those are like the shortest ever seen. There's a figure in it. But still, the shortest ever seen, many of them are still resolved on 80 microsecond timescales. So it's not that they're a single bin in 80 microseconds timescale, so I don't think they're nanoshots. Of course, there are some, even if they were if they were intrinsically only a couple nanoseconds wide, which the Crab sometimes exhibits, we would have to see how much they would get smeared out along their path of travel. So I don't see evidence for nanoshots yet, unfortunately, because that would be very interesting, I agree. And the nanoshots have a similar brightness temperature, well, like you're saying, actually. They are up there in the brightness temperature we need.
Okay, Joe, super quick question, right?
Joe was a student a long time ago.
I was going to say I'm a student of the universe. I was curious about the frequency band limited aspect of these FRBs, and maybe queue it up as a question for us to discuss later. Is there a way to discriminate between something like an ambient environment, to which you alluded, versus an intrinsic mechanism?
Sorry, I missed the first half. What's the first sentence again? The frequency?
The frequency band limited nature.
You
see them at some frequencies and not others, even when you're observing simultaneously, or when you expect to see them.
Yeah. No, I think that's very interesting. So of the ones that we detected, so they're all one-offs and they're all broadband, all 24. Yeah. So that's interesting. I think in repeaters we see more, and this is okay. Subtle point. So the LOFAR Apertif co-observing, the simultaneous observing, was on a repeater, yeah, and we never saw it at both telescopes. So now you want to do this for one-offs because they could be more broadband, but at the moment the system isn't live anymore. So someone else, SKA, someone else is going to have to do that.
All right, we are out of time for questions. Please
thank you so much.
The discussion on Slack, and let's thank Joeri again.